This is for the resistors in parallel, and these are the measured results. And again, I better copy the unit in here. So these were the measured results, and then this one here is the total resistance. And if we look at that number and compare it to the other numbers, then we can see that there is really no way we could think about how we could come up with this number just by looking at these other numbers. Okay, let's see what else happens. Here's the measured voltage. So the voltage across all the resistors is the same when they're in parallel. And here's the measured current. And then here's the total current. And again, I may want to actually paste this in here. And this is voltage. Okay. Again, Ohm's law. Divide this number by that number. The voltage divided by the current. So 2.91 divided by 0.0194 amps. 2.91 divided by 12 milliamps. 2.91 divided by 11.8 milliamps. Oops, now I don't need the period anymore because I already have it in amps. And divided by 0.061 amps, and then I'm going to jot down the numbers. 150 ohms, really close. 243, round it, really close. 247, really close. 477, pretty close. I mean, even that is within 1%. And then the final one is going to be let's see, oops, okay, I guess I'll start over. Divided by 0.0489 amps, and I come up with a rounded 60 milliamps. Oh, whoops, a rounded 60 ohms. Which is basically the same number that I measured over here. Oh, here I forgot one thing, which is add up these numbers here. It's going to be, let's see, 0.4, 0.8, 0.1, that's 0.3, carry 1, that's 20, 32, 43, 49, 49.3 milliamps is the computed one, and again that is within measurement error that these two are not exactly the same but pretty close. The computed power again is voltage times current, so 2.91 times 19.4 and so on. 90.4, whoops, it's not true, times 0.0194, 2.91 times 0.0120, and so on. the total is going to be 2.91 times point, whoops, not there, my calculator. Oops, 0.142 watts is the total power. Okay, in parallel, how do resistance add in parallel? And I get to that in just a moment. Compute the total resistance and so on. I get to in just a moment as well. How do individual currents add in a parallel circuit? Well, they add straightforward. Just add them and you come up with the total current, as you can see here when you compare these two numbers. How do the individual voltages compare in a parallel circuit? Well, they're all the same across each of the resistors that are in parallel. And how does the total power of several resistors in parallel compare to a total power of several resistors in series? Well, here we have a total power of 0.142 watts, and here we had a total power for series of 0.00933 watts, so quite a bit less in series than what it is in parallel, or quite a bit more in parallel than what it is in series. In fact, in a parallel circuit, you get the total power to everything you put in the circuit, all the appliances, in this case all the resistors. In series, you get only a little bit of the power to them. The total current is relatively small, as we can see, and they all have to share the voltage, while here they all have the nominal voltage from the battery. By the way, the reason that this one here is 3.01, 2.91 instead of the former 3.01 is because I had left the circuit on for a few hours and then came back later and noticed, oh, okay, it drained the battery just a little bit. And in any case, the total current is relatively high when you put them in parallel, which also means that when you have appliances in parallel, such as in your house, that it increases the current, and therefore you need circuit breakers, because at some point the total current could potentially exceed the current for which the wires are rated, and all of a sudden you have an electrical fire. So in a household, everything is in parallel, but you have to pay attention to that the current may be just too high. Why are they not in series? Well, you notice that earlier, as soon as I turn a switch off or take a resistor out, nothing is working in a series circuit anymore, so you cannot put appliances really in series. You have to put them in parallel. In any case, let's answer these questions here. How do resistances add in a parallel circuit? And that's what the footnote is about. So I'm just going to see that I copy this footnote. There we go. And actually, I will put that to the next one. There we go. Add the reciprocals, and then for this one here I have to put in the numbers. Well, that one, when you look at these numbers here, as I said several times already, that you just wouldn't be able to come up with 59 unless you do know how to do it. In this case, I have to give it away. You can't just look at the numbers. I have to give the correct formula away. So let's see what we come up with. This one here is 149 ohms. And I need those ohms here. There we go. Fortunately, due to the edit, this is taking quite some time. And then of course I don't have a fifth resistor. So I add the reciprocals of these numbers. I'm going to move this a little bit up here, so I have both the numbers as well as being able to use the calculator. So 1 divided by 149 plus 1 divided by 242 plus 1 divided by 246 plus 1 divided by 473. Enter 0.0170 is the result. 0.0170. Notice that the unit is in the denominator though, so I'm going to do this ohms to the -1, because that indicates that it's in the denominator. And when I look at that, well, that's not what this number is, not the same as this number here or that number here. Well, because the original total resistance or equivalent resistance here on the left hand side is in the denominator itself, what I have to do is I have to invert that again. So invert again, and 1 divided by 0.170, and at this instance I'm allowed to write ohms because that will be in ohms. So 1 divided by that result is 58.75 or 59 ohms rounded. So 59 ohms, which compares nicely to what was measured, what was calculated over here from these two measurements. So that's how resistances are added in parallel as their reciprocals.